Good afternoon and welcome to this month's webinar on disinfectant efficacy testing. Before we start the webinar, just some housekeeping with you. If you have any technical issues, please send a short message in the questions box, which you should see on the right-hand side of your screen. During the webinar, RSSL would like to invite you to ask questions, also using the questions box. At the end of the webinar, time permitting, we'll try to answer as many of these as possible. Any questions we don't get round to answering during the webinar, we will answer offline and I'll share them with you along with the slides. So, as I said, today's webinar is about disinfectant efficacy testing. So my name is Annette Russell and I'm the sterile and non-sterile microbiological lead at RSSL. I've worked in the commercial team at RSSL for over 6 years, connecting our clients with our technical experts to support them in a wide variety of projects. RSSL can support from early phase R&D of drug product through to commercialization, as well as supporting you during the manufacturing process. If you want any further information, please feel free to contact me using the details that you can see on your screen now. For those of you who are new to RSSL and these webinars, who are we? RSSL has been around for over 30 years and we're based exclusively in the Reading area. For those that don't know where Reading is, it's about 40 miles west of London and Heathrow. We have over 250 scientists working and supporting clients in a variety of technical areas. And we have won many awards for our flexibility as a CRO, but also for our culture of supporting and developing our staff. RSSL's diversity means we're able to support a diverse range of biological, microbiological, chemical and physical analytical services across all phases of clinical development through to commercial release, supporting many different client projects to meet regulatory requirements, such as the new Annex 1. This includes supporting clients' disinfection validations, around which this webinar will be featuring, be that as part of a new facility or for any ongoing validation requirements you may have. RSSL have a knowledgeable team who can advise and support you throughout this process. So that's enough of me now, and I'd like to introduce you to our guest speaker, who I'm sure you'll know already, Dr. Tim Sandle. You may have heard of Tim and subscribed to his many publications out in the industry. So Tim has over 25 years experience of microbiological research and biopharmaceutical processing. He is a member of several editorial boards, and he has written over 600 book chapters, peer-reviewed papers and technical articles relating to microbiology. Tim works for a pharmaceutical manufacturer in the UK, but also finds time to be a visiting tutor at both the University of Manchester and UCL. So over to you, Tim.
Okay, thank you very much, Annette.
Just swapping the slides over.
Do a slide swap. Okay, can you see my slides okay?
Yes, I can indeed, Tim.
Okay, brilliant. Okay, well, it's wonderful to be back with you. And we're going to have a look at a key Annex 1 topic, which is all about cleaning and disinfection. But we're going to focus most heavily on disinfection selection and disinfectant efficacy testing. So we will have a look at some of the influencing criteria that shape how well disinfectants work or don't work. And then we will look at some of the points for success and some of the practical tips around that. And then we'll look at disinfectant efficacy standards. We'll have a little look at the differences between the European and US approaches, and then trying to deconstruct these standards slightly and work out what is best for pharmaceuticals. And we'll also have a look at the regulations as well. Okay, so just before we get too deep, I think it's important to clarify the objectives and just to stand back and have a think about cleaning and about disinfection, because they are related but different concepts. And one of the things you may have noticed if you've read the relevant sections of Annex 1, that the Annex is seeking to draw quite a clear distinction between the two. So cleaning is important and it does differ from disinfection. So by cleaning, we're talking about the process of removing residues and soiling, which can be dirt, dust, protein, skin cells, and so on, from surfaces to the extent that they are visually clean. And this is important because a disinfectant won't work properly if there is soil present, because a disinfectant if a disinfectant is going to do its job, it needs to be able to make contact with the microbial cell and interact with the cell wall, the cell membrane, and often enter the cell. And soil can act as a barrier to that process. Disinfectants, on the other hand, are chemicals that will either inactivate or kill microorganisms. And there are a number of different types of disinfectants with different modes of activity and with varying effectiveness against microorganisms. And the object of disinfection is to reduce or suppress microbial presence. It's also to avoid high incidences of particular organisms of concern as well. And the presence of these, which is something that we'll return to a few times in this webinar, is that they can signal that the cleaning or disinfection regime is ineffective, or that the frequency of rotation between disinfectants is inappropriate. So coming together, both cleaning and disinfection are an important part of biocontamination control, and they are essential to the way that we will execute the biocontamination control strategy. So a little bit more about disinfectants. So some disinfectants are microstatic, so they're either bacteriostatic or they're fungostatic, and this means that they cause metabolic injury to microorganisms that halts the growth of a microbial population. And this is through a variety of means, such as interacting with nucleic acids, inhibiting enzymes, or disrupting the cell wall. But here, once the disinfectant is removed or neutralized from contact with the cells, then the surviving population could, in theory, begin to grow. Other disinfectants are microstatic or fungostatic, microcidal, bactericidal, or fungicidal. And by having the cidal element, they can destroy microbial cells through different means. And this is through irreversible physical or chemical changes. And here disinfectants are often divided into two groups. So we have the non-oxidizing disinfectants, and these tend to have a more specific mode of action against microorganisms. And they generally have a lower spectrum of activity. And within this group, we have the alcohols, the aldehydes, amphoterics, acid anionics, biguanides, phenolics, and the ubiquitous quaternary ammonium compounds. And these are all non-sporicidal disinfectants. With the oxidizing disinfectants, these have more non-specific modes of action against microorganisms and a wider spectrum of activity, and most are sporicidal. And within this group, we have things like halogens, peracetic acid, hydrogen peroxide, and chlorine-based chemicals. We also have regulations. So there are some parts of pharmaceutical GMP specific to cleaning and disinfection, and some of those that are more pertinent to pharmaceutical manufacturing are the US Code of Federal Regulations, and I've broken down the key parts that make references to different elements of cleaning and disinfection on the slide. And there's also reference made in the FDA Aseptic Processing Guide and the PICS recommendation on aseptic practices, and then with the revision to Annex 1, the text on cleaning and disinfection has increased from under a third of a page to 2 to 3 pages. And there's also a very useful chapter in the United States Pharmacopoeia, which is chapter 1072, which gives some good background advice on disinfection, particularly disinfection selection. One thing that the regulations tend to share is the concept of rotation. So whenever we're talking about disinfection, this is always in the context of 2 or 3 disinfectants used in some form of combination. And the argument for this is that by rotating with 2 different disinfectants, then the possibility of organisms that appear resistant in some way to the cleaning and disinfection process is reduced, and this is not a factor of innate resistance, but is something that could occur if we don't have sufficient spectrum of activity to address a range of microbial cell types. So the concept of rotation only makes sense if we are using disinfectants of different modes of activity. Because if we're using similar disinfectants, then that kind of defeats the object. So we might be pairing a quaternary ammonium compound with a phenolic, for example, which would give slightly different coverage. Into the revision to Annex 1, there's also the requirement to rotate regularly with a sporicide. And there's an argument to be had about whether the best practice is a non-sporicide rotated with a sporicide, or whether 2 non-sporicides of very different modes of efficacy are then also rotated with the periodic use of a sporicide, and that's going to be very much data dependent and field trial dependent. So it's a little bit further with the changes to Annex 1. I mentioned that the whole section on disinfection has been expanded. The need to rotate between the 2 different disinfectants remains, and there's this requirement for the inclusion of a sporicide into that rotational regime. Reference is also made to disinfectant qualification, and the inference is that this is something that needs to be carried out within each facility, not least because there are different types of microorganisms and there are different types of surfaces. And there's also reference made of the importance of assessing the bioburden of non-sterile disinfectants and the need to assign expiry dates to all types of disinfectant. We also have references to cleaning as well. And there's a comment that cleaning needs to be undertaken prior to the use of each disinfectant. My personal view is that this is something for discussion. I'm not sure in areas with very, very low soiling and very, very low bioburden, it's always necessary. And for me, there should be greater emphasis on residue removal and trying to avoid 2 different disinfectants from interfering with each other. It is probably more important, particularly in aseptic areas, but we do need to make sure that surfaces are clean and soils are minimized or removed in order for disinfectants to work well. So we have these things to grapple with as well. So now, before we move into efficacy testing, I think it's important to understand the factors that will affect how well a given disinfectant works, because a number of disinfectants might appear to be well formulated. You can read the instructions on the disinfectant, but different manufacturers' disinfectants vary, and a theoretical formulation of chemicals doesn't necessarily mean that that disinfectant is always going to work well in the field. So there's all sorts of factors that need to be grappled with, and we're going to have a variation depending on the types of microorganisms that we want to kill and the population of those microorganisms. So we have the intrinsic bioburden. We also then have factors like the concentration of the disinfectant. So disinfectants that are too dilute or too concentrated will not work. The contact time, the type of surface and its properties, the hardness of the water used to dilute the disinfectant, the likelihood of organic materials or degree of soiling being present on the surface. So these are all other things to take into account, and we'll have a look at some of these next. So let's begin with microorganisms. So I've put on here the sort of classic resistance schema developed by McDonnell in the 1980s. So the first thing we have is the number of microorganisms. So it makes sense, and it's borne out by studies that the fewer the number of microorganisms, the easier it is to kill them. So a lower bioburden is easier to disinfect, all other things considered, than a high bioburden. We also have the type of microorganism, and some microorganisms are more resistant than others. So as a general rule, gram negatives are harder to kill than gram positives, and that's because they possess an additional outer membrane that acts as a barrier to the uptake of disinfectants, and this happens to be lipopolysaccharide, which is also the primary source of endotoxin. Mycobacteria, not particularly common to clean rooms, but have a additional degree of resistance due to their waxy cell wall. Fungi in general, but not as an absolute rule, are often more resistant than vegetative bacteria. But towards the top of the list, if we disregard prions, then bacterial spores are the hardest to kill. And that's because the spore coat, the spore cortex, act as a very strong barrier. And there are 3 or sometimes 4 barriers that a disinfectant has got to get through. And the difference between a disinfectant working against the vegetative cell compared to a bacterial spore, without meaning to be too crude about it, is the difference between a grape for the vegetative organism and a walnut for the spore organism. We also have a location of microorganisms. So microorganisms will either be free floating in fluids, or they will be permanently bound to surfaces, or they'll be in a mid state where you get a form of reversible attachment. And the stronger that microorganisms are fixed to a surface, then the harder they are to kill. So that's often a consequence, partly of the type of surface, but for how long the microorganisms have been in contact with a particular surface. Concentration, which I've mentioned, but is important because all disinfectants have a set concentration range, and that's the proportion of the chemical to water. But too dilute, then there's no efficacy. Too concentrated, and the microorganism won't take in the disinfectant. Contact time is the time taken for a disinfectant to kill the microorganism, and the contact time only starts once the disinfectant contacts the microbial cell. And the times vary with a lot of disinfectants. You're looking at 1 to 5 minutes, but you can sometimes need far longer times. With temperature, with the disinfectant efficacy tests, which we'll come on to look at, it's important to note that these tests tend to be carried out at around 20 degrees Celsius, so they take place at a set temperature range. Yet we know of a factor called Q10 that effectively says, it's a general rule of thumb, but there's a lot of merit in it, that every 10-degree rise in temperature halves the kill time, and every 10-degree decrease in temperature doubles the kill time. And I've put some thoughts about this as on a blog post on the RSSL website. But something to take into account is the use of disinfectants in cold rooms, where often the contact times will double that of any ambient rooms. And then we have types of surfaces, and there is a variability in the type of surface in relation to different disinfectants. So, for example, one piece of research looking at bacillus spores on aluminium found they were harder to kill than the same spores on stainless steel. We mentioned surface cleanliness, but I think it's worth pointing out as well that this is particularly important for sporicidal disinfectants. Most of the sporicidal disinfectants are especially weak at penetrating soil. And it also stands that mechanical action is really important. So the ability to kill and the speed of kill accelerates through mechanical action. We also have another variable with aging facilities and older surfaces, particularly where those surfaces become scratched and you get microorganisms residing in crevices, then contact times also tend to increase. And on the subject of contact times, another important thing to bear in mind is that when we're running disinfectant efficacy tests, often we're doing so under idealized conditions within the laboratory. And what happens in the laboratory is not necessarily replicated in the clean room. So we might test a disinfectant in the lab and we have a very nice sort of 5-minute contact time and everything looks good. Take it into the clean room where it's drier and you've got faster air change rates, and that surface may only remain wet for 3 minutes, which means to achieve the contact time, the production personnel would need to make a repeat application. That might be fine in theory, but probably isn't going to be very popular with the production staff. So time is not necessarily a fixed constant between what goes on in the laboratory and what happens out in the field. It's also important to consider stability as well. So once made up, how long does a disinfectant remain active for, and what happens towards the end of its use? And this is particularly important with ready-to-use disinfectants and also with concentrates, and particularly using the bucket system. Okay, so we now move on to look at disinfectant efficacy testing. So there are different global standards, and unfortunately with a number of things in the pharma world, this is another area where there isn't a common standard. However, and we'll look at these differences in a minute, but the standard approach for disinfectant efficacy testing or disinfectant validation, depending on your preference, there tends to be a form of suspension testing. There tends to be a form of surface testing. And there is a very important requirement to undertake a field trial. Where the standards differ, it tends to be in areas like recommended microorganisms, acceptance criteria, the size of surface coupons, and so on. And approximately there's a divide between the North American standards, which are the AOAC and ASTM methods, and the European standards. With the US standards, then there are set carriers, nominally based on stainless steel, and then with the option to use other surfaces upon which organisms are deposited and then dried, and then the disinfectant is applied for a particular exposure time. And then once the required contact time has been reached, the carriers are transferred into a liquid medium with a neutralizer, which stops the disinfectant activity. So the concentration and contact time can be best evaluated. With the European approach, there's an earlier emphasis more on suspension testing, which we'll look at in a minute, and then with surface and field trials. But with both approaches, the surface test, or the hard surface carrier test of your preferred term, is far more important than the suspension test. The suspension test is only of limited value, and this is something which the Annex 1 revision has also emphasised as well, and has put extra weight towards the evaluation of surfaces. But let's run through these main forms of disinfectant efficacy testing. So the basic suspension test, sometimes referred to as the kill time method, is an extremely crude test, and it's basically saying, does this chemical that we've decided to label as a disinfectant actually kill anything? And suspension test, as the name suggests, measures the effectiveness of the disinfectant by inactivating or killing a specified microorganism within a given time in a liquid suspension. And it basically involves challenging disinfectant solutions at given concentrations with microorganisms for periods of time, and then stopping the reaction through neutralization. And it can be useful. It tends to be something that's used by disinfectant manufacturers to look at different formulations, but it doesn't really bear much resemblance of the performance of the disinfectant in the actual environment. A step up from that is the quantitative suspension test. And these are trying to simulate in a little bit more detail actual conditions. And here the suspension must also contain traces of soiling, or what's referred to as interfering substances, in addition to the disinfectant. So the interfering substance of standard is bovine serum albumin, which is a type of protein derived from cows, and it's supposed to be an approximate resemblant of the type of proteinaceous material that might be present in pharmaceutical environments and which might interfere with the performance of the disinfectant. But the more important disinfectant efficacy tests, and the ones now where the pharmaceutical or healthcare facility is expected to adopt, are the surface tests. And the surface tests, or carrier tests, involve microorganisms applied to different types of surfaces, often in the form of discs of a particular size. And these are formed from the materials actually used within the facility. So the same material. So if it's vinyl of a given type and weight, or stainless steel of a particular grade, these are the same materials. And once inoculated, the carrier is left to air dry to mimic what's going on if an organism was to be naturally deposited onto a surface, and then the disinfectant is applied at the concentration under test for the contact time under test, and then neutralization kicks in order to stop the disinfectant activity any further. And there can then be comparisons between control organisms and test organisms, and the degree of reduction can be measured and expressed in terms of logarithms. And it can happen that the concentration that was evaluated in the suspension test or provided by the manufacturer might not be sufficient to pass the carrier test, or that the contact time was not sufficiently long. And these types of tests can be evaluated with and without mechanical action, depending on the degree of replication to real conditions is required. But the ultimate test of how well a disinfectant is going to work in real conditions is actually within clean rooms. And this is what's known as the European Phase 3 tests, although no standard has ever been produced. But in essence, what we're aiming for here is to take a selection of different clean rooms under a change control and evaluate a new disinfectant, which would need to be considered in conjunction with the other disinfectants that we're electing to rotate with, and the cleaning detergents as well, and to carry out a high level of environmental monitoring using swabs or contact plates. So the aim here is a statistical comparison of the frequency and isolation of the numbers of microorganisms isolated prior to and after the implementation of a new disinfectant. So we're comparing old regime, new regime, and then also between existing and new disinfectants, and this can help us set frequencies and in terms of the rotation, particularly between sporicides and non-sporicides. So it requires lots of environmental monitoring samples in order to be statistically meaningful, and that needs to be in the hundreds. Trend monitoring, and also a relatively high amount of microbial identification, because we need to make sure that we're not seeing untoward shifts in the types of microorganisms. It wouldn't be right if we have spores under control and then we start suddenly seeing a shift in spore formers, even if the buy burden, the overall buy burden itself is low. So field trials can also be useful to establish how often to clean and disinfect, how often to rotate between different agents, and also to evaluate things like residues and the degree of cleaning required, because we need to be mindful of residues, because residue of one disinfectant can interfere with another disinfectant. And it can also lead to things like sticky surfaces, can cause discoloration or rusting, and can sometimes promote untoward survival of microorganisms. So also within the field trial, we can consider the frequency of things like water rinses or wiping down with 70% alcohol as part of this process as well. So putting those concepts together, if we look at the first thing, the basic suspension test, does a pharmaceutical facility, a microlaboratory need to do this? And the answer is no, this is purely an experimental test for manufacturers. With the quantitative suspension test, to my mind, there's no requirement to do this. is still something that the manufacturer should do. However, if you're setting out to choose a new disinfectant and you're fairly open-minded with the different types you want to use, you could use this as a initial screening test to see whether there's much variation in concentrations or contact times between similar or different disinfectants. And then to support those choices, it's a good idea to audit the manufacturer so you know that their data has been generated under appropriate controlled conditions. Surface tests are a regulatory requirement, and these need to be done using representative surfaces from your facility using suitable organisms. And we'll touch upon the type culture environmental isolate discussion in a minute. And then the field trial is always a must. You can't establish your cleaning and disinfection regime without doing that. Now, with surface testing, and having said around the importance of that, before embarking on the validation, it's useful to engage with the disinfectant manufacturer and to understand their procedures and to get a feel for what might work and what might not work. Then there are some choices to be made about which surfaces to include. Now, there's going to be a range of different surfaces. I'll come on to that on the next slide. You also need to think about the contact time. There's no point the microbiology laboratory coming up with a 60-minute contact time and then expecting staff who are working in the clean room to try and replicate a 60-minute contact time. That's going to interfere massively with production schedules, will require multiple repeat applications, and probably is the sign of a not overly effective disinfectant in the first place. And you also need to understand the types of microorganisms found within the facility. And ideally, there would have been a considerable amount of trending that's gone on for a few years to understand the microbiota of the clean room. Now, with the question of surface selection, depending on what your facility is made of, it probably is impractical to use all surfaces. So you need to go through a selection process and develop a rationale for the most suitable surfaces. So if you're using different grades of stainless steel, then you need to decide on probably selecting one grade of stainless steel. And then look for the most common types of materials, probably working from the higher risk areas outwards. And the number of surfaces selected, I've seen up to 18 different surfaces. I've seen a lot of places use 10, others somewhere between the 4 to 6 range. But certainly given a typical facility, then it's more likely to include steel, acrylics, glass, vinyl, plastic, and so on. The most important thing, this is often a question that arises from regulators, is being able to defend, justify the surfaces that have been selected. Contact times, which I've already mentioned to a degree. If you look at a lot of disinfectant testing standards, some of them do talk about 60 minutes. This is obviously totally unachievable and way above what should be needed for a pharmaceutical environment. Generally, a non-sporicide is 5 minutes or below, and with a sporicide that will take longer, but really somewhere between the 10 to 15 minute range is ideal. The type of water used can be an important factor, although within pharmaceuticals tend to use purified or water for injection, so it tends to be water that's relatively soft. And the degree of soiling versus non-soiling that's built into efficacy studies is partly dependent upon how good your cleaning regime is and how much faith you want to put in the cleaning regime's ability to adequately remove the presence of soil. In terms of microorganism selection, again, with standards, and standards are always written multi-industry, the organisms listed in the standard may or may not be the most suitable. It is important to consider what you actually find, and also to include some environmental isolates. And that tends to be very much a very strong regulatory thrust at the moment. And in general terms, there would certainly need to be organisms associated with the human skin microbiome, so gram-positive cocci like staphylococci and micrococci. There need to be organisms representative of water systems, so things like pseudomonads, common non-spore formers like criniforms, yeast-like fungi like Candida, filamentous fungi such as Cladosporium or Aspergillus or Penicillium, and then for sporicidal disinfectants, fungi that are actually in the spore state rather than the vegetative state, and bacterial endospores would need to be evaluated. So again, a rationale is needed for the microbial selection element. Another important decision is the log reduction that's appropriate. Now, given that the highest level of surface contamination permitted in a pharmaceutical facility is 50 CFU, grade D surface, and we worked to 25 for grade C, and then decrease that to 5 and then less than 1 for B going into A. We're not looking for super high log reduction, so a 3 log reduction for vegetative organisms and a 2 log reduction for spores would seem perfectly reasonable. It is important to approach this with a relatively high starting inoculum because a 3 log reduction will have a very different meaning depending upon the starting point. So a 3 log reduction from a 10 million cell challenge, say, to 100,000 cell challenge, represents a relatively large log reduction, whereas an equivalent 3 log reduction from 100,000 to 10 isn't quite giving the same, and also has a greater degree of variability and inaccuracy. The other important factors, as I mentioned, for surface testing is the consideration of mechanical action, and it's obviously fundamental for the field trial. It is a very important part of the disinfection process. So wiping has been established as more effective than simply spraying. And spraying alone is generally very ineffective against fungi, or if there were spore-forming organisms present. So you need to take a lot of that thinking, a lot of the early development work, and make sure that's embedded in the field trial and then becomes the standard practice when the new disinfectant is rolled out. So just to summarize the key disinfectant validation points, I think the most important ones that come to my mind are reviewing the materials used in construction of the facility and developing a rationale for the selection of the most appropriate surface materials. To have a thorough understanding of the environmental monitoring data, particularly the types of microorganisms that are found. To then look at the disinfectants used or to be introduced and to make sure that they have sufficient spectrum of activity and combination against the microorganisms. To use surface testing to prove that the microorganisms concerned can be killed at concentrations that are readily available or can be easily made up using realistic contact times. And then to put all that together in the field. And then there's another important element, which is checking going forward and linking back environmental monitoring trends back to the use of the disinfectants. As with any aspect of validation, it's really important to document everything and to put all this together, including having evidence of the antimicrobial activity on different surfaces, contact times, concentrations, shelf lives, compatibility, residue removal, and so on. So just before we finish, there's just some other things that are worth pulling out to do around good disinfectant control. So quality control is important, and this includes ensuring that all disinfectants purchased are coming with appropriate certification relating to the supplied lot, and that the use of the disinfectants can be tracked and traced through the facility, and that other checks are done on things like expiry dates, whether the disinfectant is supposed to be sterile or not, and to obviously practice good stock rotation. It's also important that procedures have been written well, ensuring that the method of preparation is clear, documented and understood by everyone, that operators are aware of the requirements, that the validation data supports things like shelf life, the degree of coverage within the clean room, and there's not just shelf life of opening a concentrate, but also once the disinfectant is in the bucket. And also we also have environmental concerns in relation to the disposal of the disinfectant. It's also good practice to this thing I mentioned about screening for changes from environmental monitoring due to microbial profiles, and to, if new organisms start appearing, to sometimes periodically go back and challenge the disinfectants by running some additional tests to make sure that the disinfectant is still going to be effective against these more atypical microorganisms. Another important factor is with contact plates, particularly with the selection of the neutralizer for the contact plate to make sure it is effective against all of the different disinfectant residues that might be present. So it's an important decision when several disinfectants are being used, as you would do through rotation. You don't really want to be using different contact plates for different disinfectants for carrying out environmental monitoring. So seeking out the universal neutralizer is important. And this all comes down to profiling the environmental monitoring data, looking at that clean room microbiota, and particularly being concerned about things like shifts of endospore forming bacteria, sudden rises of fungi, a greater proportion of gram-negative rods appearing. And these may signal issues with disinfectant efficacy or issues with application or some other factor that's not been taken account of. And there's a lot of information that can be kind of pulled together, because you may get issues relating to certain locations, certain sample types, different times of the year. There may be greater vulnerability. And also when changes occur, like changes to room design, the operation of new equipment, shifts to personnel, occupancy levels, or problems with HVAC that cause increases in temperature and so on. Okay, so this is my final slide. So just trying to pull everything together. What we've looked at are some of the factors that influence the success of disinfection, including the importance of cleaning, the variation of different surfaces, and how all of that needs to be thought about up front and built into the efficacy program, and then executed coming out as a field trial, and then continued. And then all of that needs to come together as part of the wider contamination control strategy, and that's been the theme of these RSSL webinars. So disinfectant is a really important element, but of course there's the other things, and some of these things we've looked at, like clean room design, controls around people, and so on. So what we're doing with this webinar series is gradually trying to put together a contamination control picture, and this was the disinfectant topic, and hopefully some of the things I've mentioned, you can use that in terms of practical advice and building up your own qualification program. So thank you very much, and I'll pass you back to Annette.
Thanks, Tim. I'll just take back the so I've got some questions that have come in during the talk, so if I ask those now. First of all, what is the most important test when assessing disinfectants? That was from Sarah.
Okay, the most important test, it's a very interesting one. I mean, ultimately the most important test is the field trial, because that's establishing what's really going to happen in practice, but it does take a long time. You have to put up a lot of data. Surface testing is arguably slightly more important, because that's the test where you can play around with all the variables. It's where you're trying to get the right concentration at the right time. You're looking at different surfaces, different application techniques. If you get all that right, then when you roll out the field trial should work fairly well. So although the field trial is like the last step, I'd probably say the surface testing, the coupon testing, is the most important, because that's where most of the variables come in.
Okay, I see. And then we have a question from Hugo about contact times. He says, with regard to contact time, if you do a spray and wipe, does the contact time end as soon as the wipe is performed?
No, it doesn't. The wipe helps start the process off, so you're ensuring greater coverage and also helping to remove some particulates and things. But the contact time is the time of the surface remains wet, when you're hoping that the disinfectant is interacting with the microbial cells that are present.
And then following on a little bit from that, from Sally, she said, what sort of disinfectant efficacy test would you use for impregnated wipes?
That's really interesting. So the first thing is you do need to be careful with impregnated or pre-saturated wipes. So the first question to ask any supplier is any claims that you've made around those, are they actually for the disinfectant as part of the wipe? Because what it shouldn't be is where the disinfectant solution's been tested independently, because you're going to get different amounts released from the wipe. So you're going to get variations in volume and contact time and concentration. But there are some wipe tests that are available as European standards, which allow you to deposit organisms onto the surface and then to undertake wiping motions. It's very important to standardize those motions, and you can replicate that either with the impregnated pre-saturated wipe or with the spray onto the wipe method, and that they can be useful. Another important thing with wipes as well is always to be mindful of how well they've been made as well. So some wipes can release fibers or particles. So the material of the wipe is really important for its release and risk of fibres, so release of disinfectant and risk of fibres, but also things even like the quality of the edging as well, and so on. So some wipes are best suited for aseptic areas, others are better suited for lower grade clean rooms.
And I guess that would be the same for the wipes that you'd use with a spray disinfectant.
Yes, absolutely. Yeah, very similar, very similar concepts. And there's a thing in Annex 1 which kind of also connects with things like environmental monitoring as well. Simply doing these things can also be sources of risk and contamination. So we do need to sometimes tread a careful balance, particularly where we're interacting with grade A zones, that we're not, by doing what we're doing, actually introducing contamination in an attempt to sample or eliminate it.
I then have a question from Chris, who asked, how many different surfaces would you normally qualify?
It kind of depends on the facility and what it's made of, and how well you can kind of put a matrix together. But between 6 and 10 is probably where you're looking. The biggest challenge that often arises is with legacy facilities where either nobody wrote down exactly what the facility is fully made of, or certain materials were used, developed by companies that are no longer in business. So that becomes a little more awkward. It's easier with a new build because you can keep appropriate samples of the different surfaces. But generally, you're going to look at steels and aluminium, plastics, acrylics, vinyl, other materials like Trovex and things like that. Materials that are totally unsuitable are things like painted surfaces. They have no role in a clean room, and they're really hard to pass against the efficacy test.
Right, I understand that. Right, I think that's all we've got time for. But thank you very much, Tim, for your time and very informative webinar. Thank you for all of you out there listening. I hope you found it useful. We appreciate the questions you asked. As I mentioned at the beginning, any questions we didn't cover during the Q&A session, I'll forward on to Tim, and I will pass those along to you along with a copy of the slides. If you wish to catch any of our previous webinars or to catch up on Tim's blog or regulatory update, please go to our website or keep an eye on our social media posts. Our next webinar, as Tim said, is building up our Annex 1 portfolio, if you like, is on just after Easter on the 19th of April, and is about designing a cleaning validation strategy. Spaces are limited, so don't forget to register now. And it'd be remiss of me if I didn't mention that we also have some relevant training courses coming up over the next few weeks. Details can be seen on this slide, but more details can be found on our website. So finally, if you have any questions or you would like some support with any of your microbiological testing or any other testing that RSSL can help you with, please don't hesitate to contact me. But I'd like to take this time to thank you for listening and look forward to seeing you on our next webinar in April. Thank you.
Thank you.